So we've talked about differential amplifiers. We spent a fair amount of time thinking about the differential signaling and differential amplification. And one of the keys to differential signaling and differential amplification was that you have a current source that basically you have two amplifiers, typically two common emitter or common source amplifier, although it's not limited to that. You can actually have different kinds of differential stages. You can take a common base and turn it into a differential stage. You can take even a follower and try to turn it into a differential stage and do differential signaling with that. So that's not fundamentally limited to the common emitter or common source. But that's the most commonly used one because it gives you gain and common mode rejection at the same time. So one of the things that, so basically if you look at it, for example, in the context of BJT, and we'll do the MOSFET as well in parallel as we go, we have a stage. If you do a common emitter based differential amplifier, that looks like this. So you have a common source, basically you have a current source that's shared between the two stages, and then you had two resistive loads, RC, RC. You have an equivalent one. You can draw a MOSFET version here if you want. We can just leave it here for now. Or you can do it with any kind of arbitrary three-terminal device. And this is the essence. So in MOSFET, it would be RD. RD, this would be called ISS. There could be some resistance RSS here. These are the W over Ls. And we talked about that if you want this to operate properly, you want them to be matching well. So the two transistors need to be matched. We talked about different ways of making them match well. We talked about common centroids, for example, structures that allow you to make this differential pair match better. And there are different variations on that that allows you to get different levels of matching and accuracy. But anyway, so this was the essential stage. And one of the things we did, we said, okay, well, you can, if you have an arbitrary input, you can break it into two segments. You can say there's a differential part. Any two arbitrary input could be broken down VID over 2 and negative VID over 2. And then there was a common mode part, right, which you can show as VIC and VIC, which would be the same on both sides. And one of the things that we did is that, okay, if you have this antisymmetric element, the red, which is the antisymmetric, the differential signal, what it does, it creates, we saw that from a small signal perspective, this node would be a what we call differential ground or virtual ground. And as a result, because it basically one side goes up by the same amount that the other side goes down, again, from a small signal perspective, this becomes a virtual ground, and by substitution theorem, we said, okay, if it's not moving, you can replace it with a voltage source of the same value. From an AC perspective, it would be a voltage source of 0 value. So this resistor becomes unimportant. Stuff here becomes unimportant. This reduces to an equivalent half circuit. So this would be VOD over 2 and negative VOD over 2. So you can take one of these half circuits and say, well, the differential equivalent half circuit looks like this. So this was VID over 2, and this is VOD over 2. And the gain of the stage is the GM of this transistor times the RO, the total resistance you see. So if you think about this, this current then is going to be GM VID over 2, which is pulled out of that node. The total resistance on that node is resistance looking up, which is RC, resistance looking down, which is in this case RO. And it would be, the gain would be negative GM RO parallel with RC. Right? Yes?
And if you put the output, the differential output, like should the polarity be reversed for its inversion?
Well, it's a matter of definition, right? I mean, so I said if this is plus, applied plus minus, this is a taken plus minus, and that becomes an inverting stage. It's a good point. I mean, it's more of a matter of convention, the way it's defined. But this convention allows this gain to be actually, makes it inverting. Now, if I take my output the other way, then it becomes non-inverting. And that's one of the strengths of the differential amplifiers. Depending on the way you connect it, you can turn it into an inverting or non-inverting amplifier. And it wouldn't affect its performance. It would still perform exactly the same way, but it would be connected a different way. So it's just more a matter of convention of how you define it, but this is the more conventional way because this kind of translates to the VI-VO relationship that you have for a single stage. But yeah, I mean, there's nothing fundamental about that. Yes?
Do you draw the top of the RC as a ground, or do you draw it as a voltage?
So that's a good question. So he says, well, should I view this as VCC or not? This is really a small signal analysis, right? Because what we are doing is small signal. So this is really ground. So that's a good point. Sometimes I just draw a constant, basically implying that from an AC perspective it's ground. But yeah, that would be a better way of drawing it. Good questions. Any other questions? Okay, so that's a differential equivalent half circuit, right? Now you can also have an equivalent half circuit for the common mode, right? So you can say this is VOC, this is VOC, right? The blue stuff, the symmetric mode. The symmetric mode, how would that look like? I mean, we did this breakdown again. Again, from an AC perspective, the constant current source is going to disappear. What we did is that we saw that we could split this resistor into two resistors of twice the value. So we can make this 2 REE and 2 REE. And if this really bothers you, you can keep this here and then make it open circuit. But sometimes you just basically take it out. But if it's there, so this is IEE. So this from a large signal perspective is still the same circuit, right? This is exactly the same circuit. Nothing has been happening. And from a small signal perspective, this disappears. And then when this disappears, what you see is that basically there would be the question you need to ask yourself is that which way is the current flowing from left to right or right to left? And the answer is that it can go either way. And what happens is that the only thing that kind of satisfies that and the image in the mirror is 0. So this current has to be 0. Then so this current is 0, or small signal rather. And if it's small signal 0, then you can replace it with a current source of 0 value by substitution theorem again, which basically means that you have open circuited. So you can actually open circuit this and nothing will happen. Of course, from small signal perspective, this will be gone anyway. So you can see that these two half circuits separate. But the half circuit you end up with is a different half circuit, right? Or equivalent half circuit. So the half circuit for a common mode, it would be, and exactly the same thing happens for MOSFETs. So there's nothing fundamentally different. And this would be VIC, and this would be VOC, the common mode, the symmetric mode. The anti-symmetric mode is the differential one, and the symmetric mode is the common. And again, now we know how to calculate these gains, right? I mean, we know that's why we spent a fair amount of time understanding these individual building blocks, because that's what everything boils down to eventually. So it's the total resistance in the collector to the total resistance in the emitter, or total resistance in the drain to the total resistance in the source, or total resistance in terminal 2 to terminal 1, et cetera, et cetera. So it is going to, the gain of this thing, obviously on the top was, so AV differential was negative GM RO parallel RC. If you wanted to think about it roughly, if RC is much smaller than RO, GM RC. And here, AV common mode is going to be roughly the ratio of RC divided, there's an alpha there, but we'll drop it, divided by RM plus 2 REE. More accurately, it's alpha RC divided by alpha RM plus 2 RE. Yeah, but we won't worry too much about that stuff. And then this you can also write it as negative GMRC divided by 1 plus 2 GMREE, a more textbook version of writing this expression. And of course, from these two we saw last time, and these are nothing new, CMRR, the common mode rejection ratio, which is defined as the ratio of the differential gain to the common mode gain, which makes sense, which is the amount of suppression that you get, how much you amplify the differential and how much you attenuate the common mode is basically defined as this, and in this case you will get 2 plus GM REE. 1 plus 2 GM REE, roughly, if REE is large, it's going to be 2 GM REE. So you can see the size of this, the output resistance here that you present, that this output, the output resistance of this the current source is essential. And it makes sense because if this current source purpose was to keep this total current constant, right? So if there's a common, if something that changes in both of them, neither one of them change their operation point or current, and therefore the output voltage doesn't change. And the less of an ideal current source you have, the smaller these resistors are, which is the one resistor really, the same thing, the lower this effect will be. So we saw that, and that was the basis for the kind of basic operation. The next question is, how do we increase the gain? We did some gain calculations, right? So for example, I'm picking some very nominal values. Let's say if this were, I don't know, 1 milliamp, right? What is your GM for each transistor? Well, each transistor, yes.
So what if in your problem you have a completely perfect ideal current source, so RE infinity,
Okay.
and this ABC just 0?
So your question is that what if the current source was really ideal?
Yeah.
Meaning these resistors are infinity.
Yeah.
So what would happen in that case? Would you have any so if you didn't have any channel length, any early voltage or channel length modulation, right? Your voltage cannot change here. I mean, even if you did, if you have a current source that's fixed, there's a true current source, these two currents cannot change unless there's a differential voltage. So let's say the differential voltage is constant, right? So if I move it up and down, as long as these transistors are in the forward active region, there would not be a significant current drawn from the input terminal, the base or the gate, and therefore these two currents will remain the same. So your common mode rejection ratio is infinity in that case.
ABC is just 0.
ABC would be 0, yeah.
How do you draw it if it's an open on the...
You mean, like, how would you draw this? You draw it like that. I mean, if any of these things bother you, put the resistor and take the limit to go to infinity. Yes?
So why are you doing the CMRR with the half circuits? Because if you're taking the output differentially, ideally, I mean, there's no mismatch in the circuit. So the common mode gain, I mean, there should be nothing for the common mode.
Okay.
Yeah, why the half circuit instead of...
Okay, so that's a great question. So the question is that if I'm taking my differential, so half circuit is basically just capturing the essence of the differential operation, right? So what really I should have written, which I didn't, is that I should have said AV differential, which is equal to VOD divided by VID, which is also equivalent to VOD over 2 divided by VID over 2, which is what's happening here, is that. So that's one aspect. But then the other question is that, why do you care? If you're taking the output differentially anyway, you would not see any of the common mode, right? If there's no mismatch, yes, exactly. So that's exactly right. So there is another element, which is the conversion of the common mode to differential, which we haven't talked about yet, but we can talk about now. So the idea here is that in the absence of, if they were perfectly matched, the two sides, right, you will not see any effect on the differential. So as long as you're amplifying your signal completely differentially and carrying it through, it's not a problem. So there are two situations where this is not important. This becomes different, and both of them are important. One is that if you're, at some point, you're not taking your output fully differentially. What if you're taking one of the output at some point? And we'll see examples of this. There are, for example, a classic op-amp has a differential input, but has a single-ended output, right? So then you have to really worry about how your common mode is changing. The second one, which is what you pointed out, is that if there's mismatch. So we can actually talk about that. Let's talk about it. Let's pick a new color, I don't know. Let's say this is plus delta R. Let's make that, right? So if you have something like this now, so let's say one of the resistors is slightly different. Let's see what happens. So if you have one of the resistors that's slightly higher, what happens is that on this side, from the input perspective, if the early effect is not strong, still you're seeing the same behavior, right? But from the output, the same current would produce a different kind of output. So on this side, you produce what is basically GM VID over 2 times RC, right? Minus sign. This is the voltage you induce here. But on this side, you will induce, so let me just get rid of these, negative GM VID over 2 RC plus delta R. So now, as you can easily see, there is a differential. So this would be plus. There's in addition to the differential element, there is another component here, right? Which is fine for now as far as differential is concerned. But now if you had a common mode that's applied to these, what would you see on this side? The common mode induces on this side a negative, well, let's write it that way. It induces negative GM RC over 1 plus 2 GM REE times VIC. And on the other side, you induce negative GM RC plus delta R over 1 plus 2 GM REE VIC. Now you can see that even in the presence of a purely common mode signal, you have induced a differential component, which is this. Right? This is called common mode to differential conversion. Because basically the mismatch has converted your common mode to differential mode. And if you're and now once it's converted to differential, you can't get rid of it. Because the circuit cannot differentiate between them. It's already become part of your signal. Now, it is still attenuated by that factor, the common mode rejection ratio, essentially, right? But it is there. And that's why common mode rejection ratio matters, because it even appears here in that conversion. Did I answer your question?
I mean, I see with the mismatch, but in the ideal case,
right.
You redefine your differential with the OD over the ID, and in that case, shouldn't your common mode gain ABC then also be taken across the two output terminals, in which case it would be 0, and your CMRR would be at infinity for the ideal case?
No, but so remember, in a common mode case, the output voltages are the same if you had ideal case, right? If this is going up and down, this is a symmetric mode. So the two VOCs are the same.
Right.
So the common mode gain is defined as the ratio of VOC to VIC.
So you're not going to take it. What I'm saying is for the differential output, you're saying the OD over 2, and this is the taking it differentially across the two outputs over the differential.
Correct.
So
but
shouldn't you also apply that for the common mode?
no, but for common mode, what I'm trying to calculate, let's think about what physically we are trying to calculate. We're calculating, if I start wiggling both inputs together, how much fluctuations or wiggling do you see on the output? And if you're doing it together, if the circuit is ideal, if there's no mismatch like this, by symmetry, the outputs need to move together too, right? So it's a question of the ratio of that fluctuation on the outputs that are moving together to the fluctuations on the input, and that's that definition. So this is really the definition of the common mode gain. We define it that way for that physical. Now, granted, all of these issues pertaining to mismatch and all those things and conversion of the common mode to differential is there. But if you're thinking about purely common mode, it's a different representation. And this really goes back to, you remember we said any two arbitrary inputs could be broken down into an equivalent circuit like this. This was VID over 2, negative VID over 2, VIC. So this was V1 and V2. So we are applying superposition, essentially. We are applying these two once, and then we are applying this separately. Right? And when we apply that, you can see that these two are shorted. When you are applying VIC, these are nulled. So they would be basically applying the same input to both, and therefore by symmetry, the same output will be present on both outputs. Any other questions? Okay, so now let's see what kind of gain are we talking about, right? Let's say we say IEE a 1 milliamp. So what kind of GM are we going to get? What is the GM of each transistor? Is it 40? It's 40 per milliamp per transistor. So if I have 1 milliamp down here, how much do each one of my transistors get? Half a milliamp. So my GM is going to be 20 millisiemens, right? This is one of the things to keep in mind. Although the expressions look the same, for the same amount of current, you're getting half of the GM in a differential pair. So you have to keep that in mind. I mean, you're breaking your current into two. I mean, dividing it into two equal halves. So for each transistor, so IC is going to be half a milliamp, and therefore GM for a bipolar would be 20, which is easier to calculate, 20 milliamps, 20 millisiemens, sorry, millisiemens, right? Or Rm would be 50 ohms. So that allows you to calculate the gain. So let's say what kind of supply are we talking about? Let's say you have a supply of, I don't know, 3 volts. And let's say this is ground. So how should I pick this resistor if I'm running at 1 milliamp? Well, I want to make sure that those transistors don't go into saturation, right? The bipolars. So, and let's say roughly this, if I had made this out of a current, this current source out of a transistor, the lowest this can go is some sort of VSAT, 0.1, 0.2. So if this is at 0.1, 0.2, this means that this can go, this voltage can be as low as another 0.1, 0.2 above the ground. So let's say it can be 0.3, 0.4 above the ground. So I want to make sure that if when all the current flows in one, what's the worst case scenario? The worst case scenario is that the state is completely steered to one side, meaning almost all of the current is going through one branch from a DC perspective. And in that case, you're carrying 1 milliamp through RC, and this voltage should not go below 0.3, let's say 0.4 volts below the ground. So that gives you a very simple calculation, right? It says 3 volts minus 0.4, 2.6 volts, divided by this resistor is 1 milliamp. In other words, this resistor needs to be no greater than 2.6 kilo ohms. Is that clear? Let me just write this down, what I just said. So let's say you don't want this to exceed 0.2 volts. Let's say your VSAT is 0.2 volts, right? Let me use a different color. 0.2 volts. So, and you don't want to have another 0.2 volts here. So that basically means that the lowest of this voltage is 0.4 volts. This was at 3 volts, right? So when all the current flows through one side, meaning that this is 1 milliamp, this voltage should be 2.6 volts, or no greater than 2.6 volts, which basically for 2.6 volts, that would be, to get 1 milliamp through something, produce 2.6 volts, that thing has to be 2.6 kilo ohms, right? So let's say 2.5 to make things kind of round and nice, right? So you're running 1 milliamp, 2.5 kilo ohms. What is your gain? Well, we calculated the GM. What's the differential gain? Let's talk about that. The differential gain. GM is 20 millisiemens, 2.5 kilo ohms. What's the gain? 50, right? So you have a gain of 50 in this. Now, can I just increase the resistance to increase the gain? Just by, instead of 2.5 kilo ohm, what if I put a 10 kilo ohm there? What would happen? Yeah, the current will be, so what if I put 10 kilo ohms here? If I could pass 1 milliamp, let's say if I had an ideal current source, what would this voltage be in the limit? 10 volts, right? When it's steered to one side. So it would be 10 volts below 3 volts, so it would be negative 7 volts. Now, I don't have an ideal current source, so I can't basically just go below that. So basically, what it means that if I put 10 kilo ohms here, this transistor will go into saturation. So it's not going to be operating properly. You put it in spice, you expect a gain of 50 or 100, you see gain of 0.1. That's what's happening. So the transistor is not really operating in the proper ranges of operation. So it seems like a dilemma, but you may say, okay, wait, how about you make this 4 times larger, make it 10 kilo ohms, but make this current 4 times smaller. That way, the DC will work out, right? Right? Do I get more gain? GM, how different would it be in that case? What would it be if I reduce this by a factor of 4? So GM would be what? GM is proportional to IC, right? It's IC over VT. So what would happen to GM if I made this factor of 4 small? It would become 5, right? It would become factor of 4 small. So it becomes 5 millisiemens. Your resistor is 10 kilo ohms. What is the gain again? Back 50, right? So we haven't gained much in terms of gain. So what happened here? Well, you lost some GM, you increased the resistance. Which one of these stages is better? You have two choices, right? It seems to be presented with two, and you can of course take it on that anywhere on that spectrum of changing one, turning that knob, right? So we had one with 1 milliamp at the tail, 2.5 kilo ohms here, and we had one with, I don't know, a quarter of an amp here, and then 10 kilo ohm here. And they have the same gain, differential gain wise, they're the same. Is there any benefit, advantage or disadvantage to either one? Trade-offs. The smaller current will have lower power dissipation. The same thing?
I'm going to say the larger current will be more robust.
More robust. The larger current is more robust. The smaller current will have. Yeah. So both statements are good statements. Can you elaborate a little bit on how it would be robust? And then we have Alex.
Like it will be less susceptible to changes in the base load.
Okay, so it will be more susceptible to variations and changes. That's correct. Yeah. Anything else? Your common mode rejection ratio goes down when my. Why does it go down? You're saying the GM is going down, right?
I mean, right below you have the equation.
Yeah. So you're concerned about the GM part of it. That is correct. No. That's good. Good. No, it's good conversation. So GM is going down, right? That's right. But this REE, where is it coming from? This is the output resistance of the transistor you use to make this. This represents that output resistance, right? What is the output resistance proportional to? It's basically, or given for bipolar, is VA over IC. So this product remains constant because this goes up and this goes down. So come on. There's something else we haven't really extensively talked about, but in the light of our model, to think about these things. What determines the speed of how fast I can move something? How fast I can shake something, right? There are two things really, right, that determine the first order how fast I can shake this. I can shake this a little bit faster than I can shake this in general, right? Or if I take this chair, it would be harder to shake it as fast. Why? This is heavier, right? What is that mass? What is that state of being heavy in electrical equivalence? It's the reactances, right, or capacitances, for example. Right? So you have a larger capacitance, it slows you down. But that's part of it. Part of it. The other thing, really more accurately, is the time constants, as we'll see. And the time constants come from the product of capacitors and resistors, or the ratio of inductors and resistors. And we'll see that. But here's what's happening. So now the other thing that controls how fast I can move this is how strong I am. Right? For a given weight. Now, what is that strength in electrical equivalence? It's the drive, right? It's the GM. It's the current. So is there any advantage, any other advantages to one of those stages, the one with more current versus the one with less current? Speed, right? Which one do you think is faster? The higher current one, right? There are two ways to see that. One is that, okay, I have more drive current. I have a higher GM, so I can move this faster. The second way to see it is that you have, for the one with the lower resistance, for the same gain, you had higher, with the one with the lower current, you had a higher resistance. You went from 2.5K to 10K, right? Which means that the time constants here are 4 times larger. These two are one and the same. You shouldn't double count. And we'll see this extensively when we talk about high frequency behavior. But, so that's something to keep in mind in general. Now, okay, so it seems that we are stuck at this gain of 50-ish, right? How can we make it better? The problem here is that where is the problem fundamentally coming from? Yet I cannot increase my resistance and increase my gain by increasing the resistance. Because that's what we need to do, right? I mean, from this expression, you can see that you need to increase RC, and at some point it becomes comparable to RO, and that's where basically you get the higher gain. Where is this coming from fundamentally, if you think about it? When you use a resistive load. Yes? Headroom, correct. And where does headroom limitations come from? It's basically there's a direct coupling between the DC and AC behavior of these two things, right? The DC drop across here is determined by exactly the same parameter as the AC performance gain, right, which is both RC. RC determines both the gain as well as the DC drop you have here. These two are defined by the same parameter, so they're strongly coupled to each other, so you want to ideally decouple these two if you could. How do you decouple them? You want something that gives you high AC output resistance, but does not limit your current. And that's a well-defined stage, really, if you think about it. It's a recurring theme, essentially, really, if you think about it. What is it? Ideally, you can think about it also in terms of load lines. We talked about this, right? If you look at this IV characteristic for MOSFET or bipolar, it doesn't matter. Basically, what you have here is that this kind of load represents this kind of load line. And as you increase R, you're making it shallower and shallower. Yes, you're getting more and more slope, where you get more variations on the output, but you're getting less and less current, because you're increasing the resistance, right? This is I versus V. So what kind of load lines do you like? You want something that's more horizontal, something that can maintain current, but does not represent a lot of fluctuations with the current, which is basically a current source. And how do we represent a current source? So we basically want to have current sources here, the same way that we did it with single-ended stages, right? Because this is not fundamentally different. This is the same thing. So if you think about this stage, and we can do it in MOSFET and bipolar, and we'll do the MOSFET shortly. I want current sources here as load, right? But what kind of current source do you want? You want something that can source current. And that would be a PMP in bipolars, or it would be a PFET in MOSFETs. So you can actually make a current source. So if you keep this as some V bias, fixed V bias, and we can talk about how this is generated, then you have a situation where you actually have something that can provide DC current, maintain the DC current, while presenting a high output resistance. So in this case, then the gain can be modified. So let's try to write some numbers. Let's say we are still running at our 1 milliamp. And so therefore, each one of the transistors, GMs would be, GMN, which would be GM, would be IC over VT, half a milliamp each, so that's 20 millisiemens. It's 1 over 50 ohms for RM. Okay, so that's the same. Now the question is, what is the output resistance? Now, of course, the gain here is determined. So if you think about it, if this is, again, what we are doing when I'm writing these things, I'm really drawing the small signal, superimposing the small signal model on the large signal model, right? So we are doing our small signal model in our heads, and we want to get used to doing that. So this is going to be GMVID over 2. So that's the current that's being pulled out of that node. That's a fluctuation. That's the small signal current. And the resistance on that node is, of course, the parallel combination of these two resistances, ROP and RON. Right? And what are ROP and RON? Well, the ROs, RON is VAN, the early voltage divided by IC, and ROP, similarly, is VAP over IC. So let's say, for the sake of argument, this is 100 volts, this is 50 volts. So let's make this 100 volts divided by half a milliamp, and this is going to be 50 volts divided by half a milliamp. So that's going to be what? 200 kilo ohms, and this is going to be 100 kilo ohm. I mean, the exact numbers really don't matter. It depends on the parameters. I want to see. So you have parallel combination. So what is your gain? If I ask you what's the gain, it's GM times the parallel combination of these two resistors, right? The differential gain, which would be 20 millisiemens times whatever, 70 kilo ohms, which is the parallel combination of these two. So gain, if I write AV differential, would be negative 20 millisiemens, negative 20 millisiemens times 70 kilo ohm, roughly, which is the parallel combination of those two. So that's what is that? You're at 1400 now. This is a substantially higher gain you can achieve with something like this. And if you were in MOSFETs, it would be less because then you get less GM for the same current, and we'll do the numbers with MOSFETs too. You will see, but you will still get higher gain than that. So that's basically what you get for this system. Now, that's basically taking the signal differentially, right, from the output. Now, if I wanted to get, if you were not even satisfied with this gain, what would you do next? What's the next? I mean, we are not going to be doing it because we've already done it. But let's say you wanted to go even beyond that from the same stage. What would you do? You need to increase your output resistances, right? We know how to do that, right? But we cascode these two, right? So we make these like double NPNs and double TMPs, and then you get a factor of beta, roughly, depending on how you do it. And then you get another, and then we'll talk about those variations soon. But again, that's basically what you get. So you can get that. Now, the other question is that, but we know, in a way, we are targeting towards, some of the things we do are targeting towards something like an op-amp. So a lot of times, what you actually want to do is to get the output not differentially, get a single-ended output. So what if you wanted to make a single-ended output? Take a single-ended output. You don't need two outputs, you just have one. Let's say something that goes to the next stage that has a single-ended input. So what do? If I need a single-ended output, the easiest thing to do is to do what? It's just to take it from one of these nodes, right? And just discard the other one. What happens if I do that? Yes?
Your gain is halved.
My gain is halved, right? Why is my gain halved? Because basically I'm not using it. Another way to see it is using the half circuit model. Because now, this is not VOD anymore. Sorry, this is not VOD over 2 anymore. This is just VOD. If this is my output, let's say. One of these is my output, right? We can define it as a VOD. So it will become VOD over VID over 2, right? So what you see here is twice the gain, because this is not here. So the gain will be half of that as a result, right? So you get half as much gain. So 1400 becomes 700. You say, okay, I'm okay with that. I mean, that's plenty of gain, sure. If it's enough for you, you can take one output and then discard the other one. Yes?
Wouldn't it also make your common mode rejection ratio worse because you have different loads?
Exactly. It also degrades your common mode rejection ratio. That's a very good point. Because right now, what happens is that whatever, okay, so let me just rephrase. Your common mode rejection ratio is still the same. But you will start seeing the common mode voltage. Because if you keep the resistor there, if you keep both resistors, right, the stage is symmetrical.
But I mean the next stages.
Yeah. So I'm assuming right now that load is not presenting a major problem. And it's a big assumption. We'll see that this is actually an assumption we have to deal with. But assuming that you have a very high impedance load that's not going to load this stage, which is not easy to do, but we'll see how to do it, fine. But yeah, you're right. If you're loading one side differently from the other side, you're absolutely right. You're basically introducing a change, delta R, that would also induce an additional conversion from common mode to differential. But you're not dealing with differential anyway. Once you take your output single-endedly, you have lost all differentiation between single-ended and common mode. You get what you get. So you're at the mercy of this factor already at that point. You don't get anything beyond that. Whatever you got already, you got it. Now, this conversion happens. But now let's say we said earlier we are going to be on this insatiable drive for gain. So we really don't want to throw away half of our gain. Can we find a way of reusing or repurposing this other half of the gain? Can we kind of reclaim it, if you will? Is there a way to not throw it away, but use it in a meaningful fashion? Because remember, if I'm taking the output only from one side, I'm throwing away the other half. Is there a way to repurpose this or reclaim this gain that I already have, it just is in the wrong place? Can we think of a solution?
Can we
inverted and added. Okay, so that's one suggestion. So you had a suggestion?
I was going to say that we use it as like the base end emitter voltage of a BJT so that we can get some sort of like
Inversion, kind of like, so it's basically like this similar concept. You're saying that, okay, somehow inverted and added here, right? That's what you're saying, which is essentially correct. So inverted and added somehow to that. Okay, how do we do that though, right? These blocks don't really exist. We have to implement them. This, by the way, what's the easiest way to add two things in circuits? Two current sources. Put them in two current sources in parallel. And the reason that's easier than putting two voltage sources in series is that the outputs of the transistors are high impedances generally, and it's basically better represented as current sources. You can also add voltages, so you do that sometimes too. But the easiest thing is basically adding currents, basically summing nodes, where you basically have current sources dumping current or pulling current out of the same node. Okay? So that's a very simple concept. But now, anyway, so let's take that. The other question is, okay, how do we do that inversion? Because again, these blocks need to be implemented, right, with transistors. At the end, we want to have something that has only transistors or resistors and things of that sort in it. You don't want things with boxes and voltage sources and current sources, because those are not the things that you can go buy or put on a chip. So let's think about it. We've looked at this stage both here and also in a different context of this current mirror, right? You can actually reflect the current. What these stages doing really is converting a voltage fluctuation into a current fluctuation, right? What if we took this current fluctuation and reflected down here? What would happen? See if we can actually do that. So what do I mean by that? So let's take the same stage at the input. So you have the same differential pair with the tail current source. You may have this, you may not have it, doesn't matter. And now you have a current. So we are not using this side. So I'm saying, well, this side I was not using. What if I mirror it back here? Reflect it back here. Now I'm using an optics analogy here, right? Of course. This current is getting reflected. So how do we reflect this? How do we actually do this? Well, one way, if it's BJTs, for example, you can use a PFET current mirror. So instead of using two, what if I use something like this? Now remember, if you ignore the base current, whatever this current is going to be reflected here, as long as these transistors are in the forward active region, because they share the same base emitter voltage. The first order effect in a bipolar transistor is that its collector current is determined by what? The base emitter voltage. So if they share the same base emitter voltage, they will, if they're in a forward active region, they're bound to have pretty much the same current, ignoring the early effect for now. So if I pull a certain current out of here, it would be, or if it's sourcing a certain amount of current, it will be sourcing the same amount of current here. Again, I'm ignoring the base current, because there will be some base current here that I'm just assuming is very small. First order analysis. And we can do a more detailed analysis if necessary. But so if going to that, so if this is VID over 2 and this is negative VID over 2, and this becomes GM VID over 2, and this would be what? Negative GM VID over 2, right? That's the small signal fluctuation. Those are the small fluctuations. So what's going to happen? So this is going to be the same. This fluctuation is also going to get reflected. Agree? Does it make sense? So this current is going to be GM VID over 2. Now look at the polarities of these things. This is negative GM VID. So I want everyone to look here. Look at this for a second. So do you agree that I can make this a plus and change the polarity of this thing? You're okay with that, right? So now look at what we have. We have two transistors, both pouring current into this node, right? Because both of these two currents are being injected into that node. Look at the polarities, right? And they are the same in magnitude. They're not the same. They are equal in magnitude. Right? They're both half GM VID. So this guy is forcing GM VID over 2 into this node, and this one, through the mirror, is also injecting GM VID through this node. So if I ask you what is the gain, what would you tell me? What is the total current? The two current sources both injecting current into this node. That's your summation, right? So what's the total current being injected into this node? GMVID, right? So it's basically sum of these two. And what is the total resistance in this node? That's how you determine the gain, right? The total impedance on this node, or resistance now, is this resistance in parallel with that resistance, right? What is this resistance looking up? It's called ROP. This is RON, right? So you have a total current of GM VID over 2 plus GM VID over 2 injected into a node with resistance of RON in parallel with ROP. So it should not be surprising if I tell you that the total gain from this differential input to this single-ended output is this. Is it clear? Yes. Well,
how does adding connecting the base to the collector in the
here? Oh.
How does that change it from the previous? Because previously base emitter voltages were also the same.
Base emitter voltages. The base emitter voltages are still the same, right? These are the two base emitter voltages. But the collector emitter voltages are not necessarily the same, right? Because the base emitter is the same. They're just they're shorted to each other. Now, so you're concerned about the base current, I guess, or no, or the voltage.
Trying to understand
How you went from that to this?
Yeah.
Okay. Here, this is truly symmetrical, right? Because these two are biased with same voltage, and they're fixed. What we are doing here is that we are saying that, well, this base emitter is not fixed, but it's the same for both of them. And you may say, well, but you can see that we've introduced this asymmetry here. The reason we have that, why should we have this connection? Why couldn't I just do this? What happens if I do that? No, yeah, it's kind of floating in the sense that it's not connected to anything. But these base currents are being, for PMP, are coming out, right? You have two things that need to provide DC current. Yes, small, but still DC current that needs to go somewhere. If you just leave it open, this will accumulate. It will just go to a voltage and it will saturate and nothing will happen. So there needs to be a pathway for this current to be drained out. It needs to be shunted out, right? So that pathway is placed here. Now let me ask you another question. Why didn't I put this? What happens if I did this on the other side? Would that work? What's the problem with that? Why does it have to be on the other side? There are a couple of problems with that, but just. So what's the problem? What is the output resistance now? What resistance do you see looking up, where I have written ROP for the previous example?
You would only see R5?
RM, actually. Yeah. Right? So that will kill your gain. Because you have an RM now instead of an RO. Because think about the T model, right? You're shorting that current source. You're just left with alpha RM. You see alpha RM? Or RM. So yes, you've worked so hard to get an RO, and then you just not only dropped it to, not even R pi, just like dropped it to RM. So you killed it. So that cannot happen on that side. So this current needs to be provided somewhere where you don't care about the impedance, which is on this side. Now what you're creating here is that by looking into here, you see basically RM. You're making what kind of a meter? A good meter for what? For currents or voltages? You're making a good current meter. You're making a good ammeter here. Because And that's what basically sucks all of this current straight into itself. And then it reflects it here. So that's basically your inversion here. Yes? Where?
Is it not negative?
Which one? I'm sorry, which one are we talking? Here?
No, AB.
Okay, so let's talk about it. Let's think about that. Let's see if it is or it isn't. If I define this as a positive negative, the way I've defined it, right? This node goes up. This current increases. AC, right? I'm talking about small signal. This node will be, voltage would be pulled down. Because you're drawing more current out of a fixed load, the voltage will go down. Right? This current increasing, now in this, on the other side, this and when this is going up, this is going down, because this is the opposite polarity, which basically means that this node is going to be going up. So remember, this is going up, this is going up. So this is non-inverting, the way I've drawn it. Now, you can easily turn it into an inverting stage by switching these two inputs. So it's not fundamental, but the way we've drawn it and defined it, that's non-inverting. It's like taking the output from here, right? This is also non-inverting. Because it was inverting from here to there, but this is the opposite polarity. So that's how your inversion is basically that negative sign is coming from, where that's coming from. So this stage is actually a pretty important stage. And again, you have a MOSFET version of that too, like everything else, or like generally, this is an important stage. So for MOSFET, it would look like this, but the analysis is exactly the same thing. There's only one, well, there's an actual advantage to the MOSFET from one perspective, which is that you don't have to worry about these base currents. You still need to provide this pathway, otherwise that node will be floating. But these currents are zero. Here, you're drawing some of this base current through here, so you have to worry about that. But other than that, this is a very classic differential to single-ended converter. So do you see any problem with this stage? Potential problem? Can you identify things that potentially you think could be a problem? Because what's happening? It's interesting. It's doing something. It's really doing this, right? What you described. Do you see any problem? Can you anticipate a problem? Yes.
When you have your, like an early voltage, then your gains are probably slightly different, and then you get some differential to common mode conversion. Yeah,
you have slightly different voltages because this voltage is like on VBE, but this voltage is fluctuating a lot. So there's one aspect there. So there's some nonlinearity associated with that. That's true. Any other problems? You have created two pathways for your signal, right? Your signal, half of your signal is going through this path, and half of it is going through this path to the output. These two pathways are not the same, right? You can easily see. If I ask you which one is going to be slower, you can probably imagine one that's slower. Which one do you think is slower? The longer one, right? And of course, it's going through the mirror, right? So one of the paths is actually slower than the other path. Just keep this in mind. When we talk about high frequency stuff, you will see that if you have systems where there are two pathways, one of them is slower than the other one, it generates a pair of poles and zeros. We'll talk about that extensively, so if it doesn't make a whole lot of sense, don't worry about it. And that is basically creating an extra pair of poles and zeros. So for example, one thing that can happen is that this pathway can basically start degrading before this pathway degrades, and therefore your frequency response behavior will have like a two-step thing. That's characteristic of a pole to zero. And when you do that, you can have like overshoots and undershoots and things of that sort happening. We'll talk about that extensively again when we get to it. But that's the essence of it. Now, the other question I have for you is that how do we calculate the common mode rejection ratio for this? If you wanted to calculate common mode rejection ratio, how would you calculate? Because differential gain, we kind of calculated it, right? Because by differential gain, we mean the gain from the differential input to the common mode output. That's the gain. What is the gain if I move the input common mode? So if we apply some sort of a, what color did we use? VIC. So if I take both inputs and yank them up and down, the symmetric drive at the input, what do you think the output's going to do, that single-ended output? How can we calculate what that output gain is? What do you think the gain is? How do we calculate it? So can we do just a basic half circuit like that before? That we did before? No, right? Because the circuit now is asymmetrical, left and right, really. We have created a little bit of an asymmetry. So what do? Well, we make observations. We see something that's happening. So if these two are moving together, let's for now assume that they don't have a very strong early effect. I mean, that assumption is not really necessary, but let's just assume that for a second. And let's say this current source is large, so if I move the input up and down together, what's going to happen is that these two currents are going to remain the same, DC-wise, because their VBEs are the same, right? If it's common mode. So if these two voltages are the same, the question is that what is the DC voltage here? Well, think about it. If this current is the same as that current, if I didn't have to worry about the base currents, then these two voltages would have to be the same. If beta was infinity, let's say in this case, in the MOSFET, right? Because what determines this voltage is really this. I mean, so in a case of a bipolar, we had ID, or IC rather, is IS e to the VBE over VT plus 1 plus VCE over VA. And in the MOSFET, in the classic MOSFET, we had whatever, mu n Cox over 2, W over L, VGS minus VT squared, 1 plus VDS over VA, or lambda, not squared. So that was ID. So they share the same VBE, and they share the same current. If current is the same and VBE is the same, then VCEs have to be the same. Now, in the case of bipolar, the currents are not exactly the same. Why? Because there's the base current. But if that's small, it means that VCEs would be very similar. So if I ask you this question, what voltage is this roughly at? Let's say if we ignore the base current. What is this voltage at? It's going to be a VBE below VCC, right? Because this is what it's a VBE below VCC, like 0.7 volts roughly below VCC. And what that does, essentially, it means that from a half circuit perspective, this voltage is the same as that voltage, right? Now, if two voltages are the same, substitution theorem tells us two nodes have the same voltage. I can connect them with a voltage source of value 0, or I can short circuit them, and nothing happens. So for common mode perturbation, I can view this as another diode connected transistor, only for common mode. Okay? Because those voltages are the same. I'm basically shorting this here. You can, if it makes you feel better, you can draw it this way. And now, what is your equivalent half circuit? So now you can do an equivalent half circuit, which looks like this. So you have this guy. You can have the REE. You have two of these transistors, so you have 2 GM. I'm just folding this. After I shorted it, I just fold it on top of itself. And then you have this diode connected guy here of 2 GM. So what do I see? What do we see here? What is this resistance? What is that resistance you see here? What do you see looking into a diode connected transistor? Rm. So basically, since you have two of them in parallel, you have Rm over 2. And your drive is 2 GM. So the question is, what is the gain of this stage? This is VIC, and this is VOC, the common mode input and common mode output. Well, we know the trick, right? The total resistance in the output divided by the total resistance in the emitter or the source. So the total resistance in the output is what?
Where did you get the PGM from?
Because I had two of them in parallel. I just basically folded these, right? So I get, what's the total resistance there? Rm over 2. And then what do I have here? I have Rm over 2 plus Ree. That's my common mode volt gain, which you can write as so if I ask you what is my common mode rejection ratio, what would you say? It's this term times that, right? Because it's really AVD to AVC. So this has a pretty large common mode rejection ratio, which is a good thing. Now if I wanted to get more gain, we can still do more of this stuff, and we'll see that later. But now, going back to the original state, of course, in general, this is the way it looks. Any questions on this? No? Okay. Let's take a quick break.